Electronegativity gives us information about two atoms and how they're bonded together. We might be able to anticipate the bond would be polar covalent, for example. The problem here is that it's quite rare for a molecule to be made up of just two atoms. So, it's important to think of a molecule's total polarity in terms of its dipole moment, and we can calculate this by Debyes. Now, this is the magnitude of the charge multiplied by the distance in the variation in the charge and its vector. Let's look at some examples. In our first example, our protagonists are carbon and chlorine. And to make it simple, we're going to ignore the effects of the carbon-hydrogen bonds here. We know from earlier calculation that the carbon is delta plus and the chlorine is delta minus, and the magnitude difference between the two electronegativity values is 0.5. So, therefore, 0.25 electron excess on the chlorine and 0.25 electron deficiency on the carbon. But now, if you look at the total molecule, we can see that the dipole moment points up towards the most electronegative area of the molecule, and the Debye value is 1.87. In the next case, we are not going to ignore the hydrogens. It's water. And you can see that we have 4 arrows where we are considering either bonds or lone pairs, and we are contemplating their electron densities. Notice that if all the individual arrows are added together, the overall result is a global arrow pointing towards the bottom left. So, there is a clear dipole moment in the total molecule towards the bottom left being the most electron-dense area of the molecule. The Debye value here is 1.85, so very similar to the first case. Next, we're going to replace oxygen with nitrogen. So instead of thinking about water, we are considering ammonia. You'll see again that we have 4 arrows, each related to a bond or a lone pair, and its relative electron density. Taking the molecule as a whole, there is a clear dipole moment with a Debye value of 1.47. So you can see that it is less than the water case. But, as it has been drawn, the upper area has the highest electron density. It's the most delta minus, if you will. There has been a clear message so far. Let's look at a more complex case. When we look at methane, and this time we won't ignore the carbon-hydrogen bonds, or there'd be nothing for us to consider, we have a slightly more difficult thought process. It's a little like having a tug of war between 2 teams of equal strength, holding a rope and pulling it in opposite directions. Thus, the rope doesn't move. In the case of methane, for example, for our analogy, we have to think about 4 teams, with each team pulling in the opposite direction to the net direction of the other 3. But there is no dipole moment, so no Debye value. It's 0. When we change from hydrogen to chlorine, we still have the same spatial arrangement. So, although if we were thinking just narrowly at the carbon-chlorine bond, it is indeed polar, if we look at the total molecule and consider the dipole moment, there is again 0 Debyes in the molecule. Now we look at ethane as well as carbon dioxide, and here the tug-of-war analogy is a little stronger. Hopefully you can spot that we have two arrows going in opposite directions. And so again, we don't have a dipole moment for the total molecule, and the Debye value is, in both cases, 0. Next, we're going to look at a double bond. In the first case, we have two carbon-chlorine bonds, and you can see that the polarity of those bonds are in opposite directions to each other. And again, it's a tug-of-war scenario. Both bonds are polarized to the same extent from the same atoms, and so we have no dipole moment that results in a Debye value of 0. Lastly, we're going to look at a very similar molecule to the last one, but we have made an important change. We've moved the positions of the carbon-chlorine bonds relative to each other. Now, if you look at the two arrows, we do have a net total vector. We do have a dipole moment that is positive, non-zero Debye value. The left side is more electronegative. So, those last two examples reinforce the importance of thinking of this as a vector.